So let's recap where we have been. And that was as far as just kind of looking at our titration curves in conceptually. Do you want something? So the first two curves that I have on the left, those are our strong acids titrating a strong base, or a strong base titrating a strong acid. I want to introduce us to a couple of new terms, or perhaps you've heard of them. What I'm titrating, the thing that's in my flask, we refer to as an analyte. And that just says that there's something we don't know about that. So this is like, we don't know everything about it. What lives in our burette, that is our titrant. So we want to analyze our analyte, if that helps you. And what we know everything about, like you'll be given the molarity, you can read on the burette to the 2 decimal places the volume of your titrant that you're using. So you can get all sorts of useful information, and you'll know the identity. And we can use all those things to even figure out what unknowns are, which is fun. And then I was telling you that on our strong acid and base titration curves that we don't have these buffer regions. So these buffer regions are right here and then right here. And our strong acids and bases, so they just either start off at a really low pH or they start off at a high pH, and then they drop down, and then when they hit equivalence, so when I have the same mole-to-mole ratio for my strong acid to my strong base, now I have nothing but water and a salt. So we are at a pH of 7. But with our buffers, because, let's see, so this would be a strong base, so I have a weak acid in here, so let's just stick with the same one that we've been doing, acetic acid, HCOOH. If this lives in my flask and I titrate it with a strong base, what am I left with? Well, don't forget it's going to be a one-way arrow because I'm going to use all of my strong base. Oops, I forgot my minus. And I'm going to end up with my HCOO. So my weak base plus water. This is going to have the pH higher. So after I've used all of that, I still have my weak base in there, so my pH is higher. If I do the reaction in reverse, if I react my weak base with the strong acid, I'm going to start off with a higher pH, and I'm going to end up below 7. And it's going to be because the opposite is true. So weak base with a strong acid, I'm going to end up with a pH lower than 7 at equivalence, and then a weak acid being titrated with a strong base, I'm going to end up with a higher pH than I expect. So we're going to run with that, and now we're going to start analyzing some of these points. There's a few really important things to keep in mind here. First of all, the equivalence has this handy definition. I'm sorry, the point 2, where the pH equals the pKa. That's half of the equivalence point. Why is that handy? Because once I can find that spot on my graph, I now know what my pKa is. So in this one, I hit that spot at 4.77. That is my pKa. And I can use that for all of my other calculations in the buffer region, because remember, that's where Henderson-Hasselbalch applies. And my buffer region then, so if I know where my equivalence point is, which is here at this point 3, and I look here and I can see that I used 25 milliliters of it, so finding my half equivalence point, or the area where my pKa equals my Ka, well, that's going to be at 12.5 milliliters. That's going to be precisely half. Cool, so I know that. And then this other handy thing for being able to define how wide your buffer region is. So you can look at it and you can kind of see, well, where the inflection really changes. So when I'm building up to it, and then when I'm getting ready to take off again. But we can define that, the buffer region, as being the 1 pH above and below the pKa. So if I look over here, I can say, okay, so this is at 4.77, so right around 5.77 is where my buffer region ends, and right around 3.77 is where it begins. So right at the curvy part. At equivalence, remember this is when I have used all of my weak acid or my weak base. So in this case, I'm titrating a weak acid with a strong base. So all of my CH3COOH is gone, and I'm just left with its conjugate base and water until I add more NaOH. And at this point, now I have excess moles of sodium hydroxide, and that's the thing that's driving the pH up. And you'll see that that's going to plateau out because we're going to approach the pH of just straight sodium hydroxide. So let's think about how we can take advantage of these points. So before I've added anything into the flask, we can think of it in terms of just a reaction with, choose a different color, with CH3, COH, aqueous, plus water, liquid, going to, and that will be in equilibrium, going to its conjugate base, OO minus aqueous, plus what? What have I done? I've donated a proton to the water, so I've made H3O plus. So that is its equilibrium reaction. So now let's think about this. What have I told you? I've told you that we can look at our spot. We can look for something on the graph that will tell us our pKa. We can find our inflection point to get where we're at equivalence. But right now, all I know is that I have 25 mils of my acetic acid. So here's my acetic acid. And I know what the concentration of my sodium hydroxide is. So with this one, I can't really write anything out at this point in time. But in terms of this reaction, this would have to be a rice table. And I can write my Ka and be like, okay, I feel like I can do that. I'm going to have my CH3 COO minus and my H3O plus divided by, let's see, my acetic acid, 3COOH. Beautiful. But without any more details, I kind of feel like I'm a little bit stuck. I want to get to the point on the graph where I can at least kind of figure out how many moles I might have started off with my acetic acid. So let's just kind of think that through. What happens if I take this, and we now know that I have a pH of slightly greater than 8, slightly less than 9 would probably be better. At equivalence, and what do I know there? I know at equivalence I had 25 milliliters, 25.00 milliliters. Oops, not 25. Yes, 25. I have 25 of both. 25.00 milliliters of 0.100 molar NaOH. Moles, actually. I'm getting ready to write something I ask you all not to do. 0.100 moles of NaOH per 1,000 milliliters. And what does this get me? It says that I have used let me do the math. 25.1 divided by 123. Helps if I type in the right numbers. 25. Yep. 0.0025 moles of NaOH. That's what I've used. That's how many moles I've used at equivalence point. So let's see how cool this is, how much we can figure out with that. So what reaction have I done? I've done CH3 COOH plus NaOH And this is a one-way arrow. It's a one-way arrow because I'm going to use all of my weak acid and my strong base. And what is this going to give me? Let's see, I'm going to protonate that hydroxide, and I'll get water plus my CH3COO minus. So what do I know? Well, at this point, I have 0.0025 moles. So at equivalence, not 8, at equivalence, I have 0.0025 moles of my sodium hydroxide. Wasn't this a 1-to-1? So by our definition of equivalence, that means I started with, let's see, let me rewrite this. I have used, thank you, 0.0025 moles of sodium hydroxide and 0.0025 moles of my acetic acid. So how do I know that? Because I have hit the point where equivalence means I'm getting ready to turn the corner. So I'm going to go from increasing my pH to that inflection point, which means that now the sodium hydroxide is taking over. So as I'm going up this curve, I'm using more and more. I have less and less and less of my acetic acid in the flask. And at this point now I'm making the turn. I'm going to just trying to exaggerate a little bit. So you can see it kind of pulling away and increasing. That means I have no more of my weak acid to balance out the addition of my base. So I know that's how many moles lived in my beaker before I started. And I know the volume of those moles because I was given that. And I would measure that in lab. I'd be like 25 mils. So I can figure out what my initial concentration is. So from here, I can be like, okay, so that means that I started with 0.0025 moles of my acetic acid. And those moles were in initially this 25 milliliters. Milliliters. And I need to convert that to concentration because I want to be able to use Henderson-Hasselbalch in that region. So to convert that to a concentration, 1,000 milliliters per 1 liter. And so what's that get me? 0.001, I believe. It's either 0.001 or 0.1. Yeah, let me just do it so I don't have the wrong number. Divided by 25. 1, 2, 3. Yep, 0.10 molar. COOH. So now I can come back to like this table, right? And I know what my initial concentration is, so I can remind myself now that I know that this initial is 0.100 molar. And that one doesn't matter. My change, well, it depends on where I am on the curve. Now remember, I told you here that value was 4.77. So what can I do with that? I know that my Henderson-Hasselbalch, say that fast, that pH equals pKa plus the log of my concentrations. So of my base over my acid. Sweet. So the log of my concentrations and then my total volumes don't matter because they're going to cancel out. So I really just need moles when I'm working with Henderson-Hasselbalch. For anything else, when I'm doing just a rice table, remember you need to work in terms of your concentrations, not just moles. But with this now, I know what my pKa is. This is 4.77. So at any point in the buffer region, I can now use Henderson-Hasselbalch because I know what the volume is that I've used, that I have, right? My 0.100 molar. And I know what the volume is that I've used of my sodium hydroxide. So remember what we were doing last week where we were figuring out how many moles we've used and then subtracting them? That's all we're going to do now. So I can come back here and be like, okay, I know what my starting was. Let's move this thing out of the way. So it's just kind of in the way. Now I can say, okay, I know what my molarity was for my CH3COH. Let's write this down so we have a note of it as soon as I can get my mouse back. So this is also 0.100 molar. I know the molarity of my sodium hydroxide. So using my volumes, I can figure out what the pH is on any point on this curve, which is very nice. So let's see what else we can do with this. Well, let me do a little bit more math with that. Let's go ahead and figure out. Let's do let's just choose 10 milliliters for fun. I want this out of the way a little bit more. I feel like I do. I'm going to erase this so it's not cluttering. All right, so let's start this. Whoa, that's not an eraser. Let's start this over and then ask ourselves at 10 milliliters. So here we're in the buffer region. What is the pH? So at 10 milliliters of NaOH, pH, what is that? Okay, so now we need to do the one arrow. We need to figure out how much of the carboxylic acid was used, and then we can get to our moles of both our weak acid and our weak base and go from there. So instead of 25 mils of my sodium hydroxide, this one here is going to be 10 mils. 10 milliliters of that. We know what my starting, milliliters, let me erase this so you don't think that's what that is. I'm sorry, starting moles. So this was 0.25. Did I really just do that to myself? 0.25 moles, if I remember correctly. Now I'm doubting myself. 0.025. 0.025 moles. 0.0025 moles here. And how much do we use of the sodium hydroxide? That's 10 times. Shush the dogs and button pushed. So this is just going from the beginning. So we'll have nothing on our water. We won't have anything anyhow. Let me do my phases. And aqueous. And now let's see, what are we going to use? Remember, the one-way arrow means that I'm using all of my moles of my sodium hydroxide. 0.001. And then this is starting at 0 and going to plus 0.001. So my conjugate base is easy enough. That's just whatever I've used of my sodium hydroxide. That's how much I'm going to generate there. But to use Henderson-Hasselbalch, I needed to actually do that subtraction. So my 0.0025 minus my 0.001, 0.0015. Cool. So now I know my moles. What I would need to do is figure out what my total volume is. So I'd have like my 10 mils plus my 25 mils of, so 25 mils plus my 10 mils to get my total volume, then figure that, change that into a concentration. But remember, I said with your Henderson-Hasselbalch, those concentrations are going to cancel out. So we can jump right into it. Plus log of base over acid. What's this give me? So my pH then, my pKa, that's not changing. This is still 4.77. So I can still use it. Plus the log of my base over my acid. So my base is this 0.001 and my acid is 0.0015. And so let's see, what do we get? Log 0.001 divided by 0.0015. So I get 4.77 minus 0.176. Let's check Sig Figs. I have 4 in my volume, and I used that. I had 4 and 3, so I had 3 here. So I'd have 3 here. Ignore these numbers. I truncated. So then I would have 3 after the decimal, so I'd want to make sure that I held on to that. But my 4.77, that's a value I've been given. That's 2 after the decimal, so I'd be truncating to 2 after the decimal here. So my pH is going to have 2 after the decimal. 4.77 minus, oops, plus 4.59. Good. So our double check there is that we would expect it to be lower than the pKa, because we haven't gotten to the point where I have an equivalent amount of my weak acid and base. But look what we did. We started with only a volume of our weak acid. We had our concentration of our strong base, and then the amount that we've used, we've taken the amount from this axis. We were able to use our equivalence point to determine how many moles we actually had of our acetic acid, and then from there work back, and we figured out pH at 10 milliliters, and now we can figure out anything in that buffer region. We are good to go. So we got a lot of information out of just a few things. So my only reminder here is that my analyte has been used up. That's what we used to determine in our previous step. So I used number 3 to get to the actual moles of our acetic acid before we even got going. So that was nice. And then past the equivalence point, now remember, can only use Henderson-Hasselbalch here, roughly, in our buffer region. So past the equivalence point, now my pH is going to increase. So this one, if I wanted to know what my pH is, I would have to figure out, so I'd be like, okay, so at 40 milliliters times my 0.100 moles of NaOH, and those moles are in 1,000 milliliters. What's this going to get me? This is going to get me the amount of moles that I actually have had access to. But remember, going back here, we lost, whoops, nope, I erased it. Yeah, the 0.0025 moles. So at equivalence, we determined that this was 0.0025 moles of sodium hydroxide and of our acid, OOH. So that means even though I'm going to have this amount of moles, I need to subtract off those 0.0025 moles that have been used. So remember this reaction at this point, I've used all of my weak acid. So anything beyond that now are just free-floating moles of hydroxide going all willy-nilly in our beakers doing what they want to do. So let's see, 40 times 0.1 divided by 1,000 minus 0.0025. So that means that I have 1.5 times 10 to the negative 3 moles of sodium hydroxide. Those moles now live in this total volume. So my flask is getting pretty darn full at that point. What do I have? I have, this is divided by my 40 milliliters. That's what I know I've added of my sodium hydroxide, plus the initial 25 milliliters that I had of my acid. And then I want to convert that into liters per 1 liter. This right here gets me the molarity of my sodium hydroxide once I get to this point. Now, as far as test questions go, I would expect you to be able to determine what's going on in here for your pHs. I would expect you to be able to use information from what's going on there as far as our equivalence point and how to use that to apply to what's going on here. And I would expect you to be able to determine, like, I don't know, like I think from here up is pretty fair game. It's pretty easy to look at those numbers instead of having to approximate something that's midway. So it's going to be something that you can visually delineate and know what your volumes are. You won't have to guess at anything. But all of those things I would expect you to be able to do. So with that, we are ready to do some practice. I'm going to post some practice problems on Canvas. Go ahead and use those. And we will do more practice with it on Wednesday. So we're just going to reinforce this idea. These are all of the same concepts we've used to now. So that's the one thing I want you to feel comfortable with, is that we haven't layered anything new in. It's just a different way of looking at it. But because we're bringing all the parts and pieces together, it's really easy to kind of let yourself get lost. So what I suggest is before Wednesday, try to go through and get a few of those practice problems on that handout that I'm going to post. And then we will return to it and work on them on Wednesday. And then that will be the end of buffers. So next week's lab will be all buffers. And then after that, we'll go into something totally new. So make sure, in preparation for the exam, that you are comfortable with this material. All right, that's it.